All right. So now having established that, now we are saying that at some point in history, these scientists had gained some knowledge on how they're supposed to kind of extract different compounds from these different plant exudates, of which opium exudate was also one of an extract where they had to isolate compounds. And so morphine in about 1803, it was extracted from this opium exudate. So we are talking about, many years ago, and in 1803, the scientists managed to extract that morphine product. They kind of removed it from this whole exudate. And you find that with morphine, which is, morphine is not so well absorbed, orally. You find that, yes, on the market, yes, we do have morphine coming in or oral, like in an oral dosage form, and yeah, then we're going to find the other type of dosage forms of morphine. But for the oral dosage form of morphine, we are told that it doesn't really have good bioavailability, or it's not really well absorbed. And then even these scientists in the 1800s, they did notice that, So, but it was until like 1853, after they came up with this hypodermic syringe, that they were now able to administer morphine like directly into the blood system, And at that time, they did notice the difference that morphine, or the effect of morphine, the difference that was there after you take morphine orally, and also compared to the effect that was coming up once somebody has been injected with morphine. All right. So, and even at that time, we have already mentioned, even at that time, after they isolated it, it was not part of that crude extract. After they isolated morphine on its own, they did some testing. They found that it was a very good analgesic, and it has these sedative action, and which were much more better, compared to the crude opium, So, and because of that, you find that in 1861, even the Americans did use it during civil disputes and the like. They did use it, but at that time they had not really understood the future, the long-term side effects of morphine. To them, they just wanted to use the good part of it, it was an analgesic, and it was sedative. So to them, they're only looking at those good effects of morphine without really looking at the long-term side effects. And this is something that we have to be to know as pharmacists in making and future scientists, which is that, yes, we do come up with different drugs, and we can have the knowledge of, somebody will come to you and say, okay, there's this plant, it has been used for years in our village as maybe for management of hypertension and the like, and people keep using it. You find that we do not really understand what the long-term side effects would be, and people would kind of try to misuse them, not even knowing the dosage form. So because of that negligence, you find that years ago, this even led to people dying. Like what happened in America, people died. Why? Because they just looked at this plant and said, okay, it has got this side good effects. They were able to use that, and without really understanding what would happen next, of which there are issues of, morphine has got these severe side effects, of it can cause a respiratory depression, which can actually cause somebody to die, instantly if it's on a higher dose. And then you talk of long-term effects of addiction, it has got issues of tolerance, dependence, and these are some of the things which were not really understood by people at that time, So the same thing also applies to our time to us right now, even as we try to look at these different trees and say they have these uh, um, pharmacological effects, we really have to study. That's why you find that for a drug to be discovered and to actually go on the market, it will take you a minimum of 10 years. Why? Because you have to study all these things. All right, so that was just a brief introduction about these opium analgesics and basically morphine. All right, so now we're going into details of morphine. What we are saying is that with morphine, it was, we are talking about years ago, like close to, is this like 200 years ago? Something like that. But anyway, decades or so. So we are talking about like analgesic effect or not. All right. So like we find that you find that with codeine, that's methyl ether. Okay, so codeine is called a methyl ether of morphine. All right, and also you find that it's also present in that opium exudate, that you are getting from the plant. Codeine is also part of that. And what now we notice that, okay, and for its use, you also find that it's going to be used in treatment of pain, management of pain, and coughs with diarrhea also. But now the catch is that with codeine, it causes a drastic change, um, in its binding to these receptors. So you have adjusted, you have removed that phenolic hydroxyl group and replaced it with a methyl. Okay, so after you replace it with a methyl group, you find that there's going to be a change in its binding to the receptors in the brain. And you also notice that this binding affinity of codeine is about 0.1% that of morphine, which is quite a very big drop in binding. So what is our conclusion? Our conclusion is that once you remove the hydroxyl group on morphine and replace it with something else, the binding affinity of the next analog is going to be altered. So which means that the hydroxyl group of morphine, the hydroxyl group which is found on morphine is important for the analgesic effect. All right. So this is the conclusion. For a conclusion, you need a free phenolic hydroxyl group for better analgesic activity, which is this one. This phenolic hydroxyl group, this is the one which is referred to a phenolic hydroxyl group. It should remain untampered with if you want your your analgesic effect to be maintained, okay, and not reduced, like what happened after you add a methyl group to form codeine. All right, and also there's also something about codeine. All right, this is just a question that I would put across about codeine. You find that with codeine, you after you inject it directly in the brain, you'll be told that it does not present with any analgesic effect. Okay, so the question would be, why is that so? So from the structure of codeine here, for it to have its better activity, you find that it will need to go and be metabolized in the liver. It undergoes all demethylation, So after it is metabolized in the liver, then it will be able to go and have an impact or its influence on those receptors in the brain. So what it means is that once you inject codeine directly in the brain, it would have not undergone or demethylation in the liver. It would have not undergone metabolism in the liver, and because of that, it will not present with analgesic effect as indicated. So that's the answer to that. So we have established the first thing about structure-activity relationship is that for analgesic effect to be maintained, okay, for your next analog, to be maintained as equivalent to morphine, you have to make sure that the hydroxyl group, the phenolic hydroxyl group, is not masked, okay? Or also you have to make sure, you have to make sure that it's not masked so that the activity is maintained. All right. So now the next, what about the next functional group? The next functional group is the 6-alcohol. So for this one, this is the one, let me just take you back to the structure. This is the one here, okay? This is the hydroxyl group here. We're saying 6, that's because that is position 6. Let me take you back on to, all right, so as you can see on morphine here, this is the position 6, this alcohol on position 6. What what is it important for analgesic effect, you know, or it's something that you can get rid of when you are trying to us to understand the importance of this 6-alcohol or alcohol group found on position 6. We are going to try and compare the activity of morphine, 6-acetyl morphine, and morphine. All right, the hydroxyl group is going to be free like that of morphine. And once it's free, then it will be able to bind to those analgesic or opioid receptors in the brain and produce the analgesic effect. Okay, so that's basically what will happen. So with having that in mind, then, okay, we are saying that this the 3-acetyl group has to be removed by the esterase enzymes, like I mentioned, in the brain. And because of that, you find that heroin will be more reactive, more powerful than morphine because it's passing through the blood-brain barrier easily. But again, it's less active than 6-acetyl morphine. Why? Because it has got an acetyl group on position 3, which has to be removed by esterase enzymes, unlike 6-acetyl morphine, which doesn't have that acetyl group there. So if you're having questions, just skip them. Then I'm going to answer them at the end of the lecture. All right. Okay. So all in all, what we are saying is that heroin and acetylmorphine are both potent analgesics, you know, and the effect is for both of them is higher than that of morphine. And then besides that, also we are saying that unfortunately, even though these two drugs are more potent than morphine, but the side effects are greater than that of morphine, you know, the side effects of tolerance and dependence. So because of that, you find that for 6-acetylmorphine, it's actually considered as a very dangerous drug, and in most countries, even its synthesis is banned. But for heroin, you find that in certain places it will still be used, but mostly in terminally ill patients, like I mentioned, because they've got this effect of euphoria, which can be appreciated by the terminally ill patients. Okay, so what we're saying in conclusion with the importance of that hydroxyl group, alcohol group in position 6. The conclusion is that the hydroxyl group, the 6-hydroxyl group there, is not needed for analgesic activity and can actually be beneficial in analgesic effect. With that, we are saying its removal or its masking, okay, of this hydroxyl group on position 6, it can actually be beneficial. How can it be beneficial? It's because of its pharmacokinetic properties, you know. We are saying hydroxyl group at position 6 is polar, you know. So because it's polar, the BB layer is kind of hindered. But once you mask it, once you remove it and add another group, you are improving the pharmacokinetic of this analog. This internet is going to kill me. Managed to buy good internet, but I don't know. Anyway, but all I'm saying is that with the masking or removing of this hydroxyl group from position 6 will help improve the pharmacokinetic of your new analog, hence promoting its quick passage through the BB layer. Okay, that's the conclusion. So it's not so it's not really needed. Okay, that's the conclusion. The hydroxyl group at position 6 is not really needed for the analgesic effect or for your next analog. All right. So now the third functional group that I want us to talk about is the double bond, which is at position 6 and 8. Okay, so that's the double bond. Is it important for our analgesic effect? This bond has been removed. An example is dihydromorphine. They will tell you that the double bond is actually not necessary for analgesic effect. Okay, so what it means is that even though you remove this double bond from your next analog, like what happened to the dihydromorphine, the analgesic effect was still there. So even if it's removed, like you can actually, it's not important for the effect to occur. All right. Then the next one is the aromatic ring. Okay. So we find that we are going to later talk about, like maybe the next class, we kind of look at different structures and see the importance of this aromatic ring. Okay. And that's when we're going to appreciate the importance of an aromatic ring in this in morphine compounds. So what it is that with an aromatic ring, it's important for analgesic effect and the analog that you are going to make out of morphine. And then the other one is the ether bridge. So the ether bridge is it's this bridge here. Okay, this is the ether bridge. So we're saying the ether bridge is not essential for activity. All right. Okay, so with the ether bridge, we are saying so with ether bridge, we are saying it's not necessary. And how is that? So we are going to notice in our other lecture of like different compounds which were formed without an ether bridge, and you're going to notice that analgesic activity was still maintained. Okay, all right. So now the other one is the N-ethyl group. Which one is the N-ethyl group? The N-ethyl group, let me take you back. This is the one here, okay? N-ethyl group. We also want to establish whether it's important for the pharmacology, the analgesic effect of morphine or not. Okay. We're going to see that with let me give an example of the compounds. So the example that I'm going to use to establish the importance of N-ethyl group is that of normorphine. Okay, so with normorphine, the methyl group there, the methyl group has been replaced. Okay, so so now let's see what happens. You find that with the N-methyl group, once you remove the methyl group and replace it with an oxide group or oxygen atom, or once you make a sort, a quaternary sort of that N position, you're going to find that then the compounds that are going to form will actually be inactive. They will not have this analgesic effect. Okay, so because of that, what we are saying is that if you remove that N-methyl group, which is there, and replace it with an oxygen atom, or maybe you make a quaternary sort, it will become the compound or your analog will be inactive once you take it. And this would suggest that N-methyl group is actually very important to be maintained, even as you make different new analogs. All right, and then we talked of normorphine. the normophine, which I talked about, and I showed you the structure. So you're going to find with normophine, even after they removed the methyl group, was reduced. Activity of actually reduced, but it was not eliminated. So comparing to what happened after you add an oxide group, said activity is removed completely. But just removing the methyl group for one atom, what it is that we need a tertiary group, a tertiary amine group to be there, so that the atom can be can be less polar and hence be able to pass through the blood-brain barrier easily and exert the effect of the compound in the receptors. Okay, so the conclusion now is that when you replace that nitrogen atom with carbon, the activity of your analog will be completely lost, the analgesic effect. And in conclusion, nitrogen atom, okay, is essential for an analgesic effect of morphine and also the different analogs that you're going to have. Okay, so with this nitrogen atom here, it has to be tertiary, okay, a tertiary nitrogen to a one carbon here, another carbon there, and another carbon there. That's why it's called tertiary, okay? So you find that with normophine, that nitrogen atom is secondary. It's only attached to two carbon atoms, that one and that one. This methyl group has been removed. And because of that, this secondary nitrogen atom is more polar. And if it's more polar, its penetration through the BB layer is hindered. Hence, the activity of this normophine is reduced compared to that of morphine. Okay? All right. And then the other last functional group that I want us to talk about is that of stereochemistry. Okay? So we're talking about now the stereochemistry of this morphine compound. So with morphine, we are saying it's an asymmetric molecule. That is, it has got the different sides of morphine are non-identical, and it has got these asymmetric centers. Naturally, it has got these it's an stereoisomer. Okay, stereoisomer. All right, that stereoisomer. So we find that with morphine, it has got two stereoisomers. It has got one like a mirror image of itself. All right. So the other image of itself does not have analgesic effect. So when you look at when you talk of stereochemistry, okay, you are talking about the same drug, same functional groups, but only different orientation in space. Okay. So you find that it can be a same drug, same everything, but the difference is that the other one is S, the other one is R. And because of that, it's going to have different pharmacological effects. And an example would be that of, I don't know if it was in your class or the other class where we talked about thalidomide, where it was discovered, and the other form of, I've forgotten whether it was D or S, anyway, but any one form of it had the desired pharmacological effect, while the other form of it was caused what? Okay, thalidomide was, when it was found, I think it was 1952, around there, I've kind of forgotten, but when it was discovered, it was being used for the management of nausea or so in pregnant women. I think we talked about it in your class. And then afterwards, they discovered that they had got the babies who were born from those mothers who were exposed to thalidomide were born without limbs, without hands, and without legs. And because of that, that is an idea of how the stereochemistry of these compounds should be taken note of. You find that one image will have different effects from the other image. So in our case of morphine, you find that its mirror image actually does not have any analgesic effect. Therefore, it tells us to say we need to maintain the stereochemistry of morphine for it to have this analgesic effect. All right. And having established that, we need to understand that for morphine to produce its effects, it has got the main important interactions that are involved between morphine and its receptors. That is, if there is an interaction with the phenol, that's where we have that phenolic hydroxyl group. There is an interaction with an aromatic ring. There's also an interaction with the amine, where we said we need to have a tertiary amine group. Okay, and having established that, so this is just an highlight of the important functional groups that have to be maintained in morphine or an analog of morphine if you have to maintain the activity. That is, we have got the tertiary amine group has to be maintained for both the aromatic ring there, and we have an hydroxyl or phenol group there, which has to be maintained. The other ones are not really necessary. The other ones are not really necessary, but these ones, okay? And these are just structures of morphine, natural morphine, and its mirror image. So I find that this is stereochemistry, okay? It's an exact same molecule, but different orientation in space. Like you can see these of morphine will actually not have its effects on the receptors. And all right, so not have any effect on its receptors. And why is that so? Oh, I hope I didn't. And why is that so? You find that with mirror image, it's in only interaction with the receptor is by the aromatic ring. Okay, and we did mention that for morphine to have its effect, well, it has to have interaction with the aromatic ring, the phenol group, and also the amine group. But with this, a mirror image of morphine is only able to interact with the receptor through the find that again changing the stereochemistry at that position of morphine, that position, once you change the stereochemistry of that hydrogen atom there, you find that the activity is going to be reduced to that 10% of morphine. So this is just telling us on how the importance of the stereochemistry is, even as you work on analogs of morphine. All right, so do we have any questions? I think that's the end of our discussion today and analogs. So now, when you talk of the variation of substituents, the first as a first design strategy for this one, it employs the use of an alkyl substituent and placing it at that phenolic group. That's the hydroxyl group, which is attached to the aromatic benzene ring. So after they did such a study, they found out to say once an alkyl group was added to the phenolic group, the activity of the new analog was it was poorly active. And also besides that, certain compounds were actually inactive. And we can ask ourselves that why was it like that? It's because from previously we did mention that morphine, for it to have its full analgesic effect, the hydroxyl group, which is connected to benzene ring, has to be free. It shouldn't be removed. It should not be replaced or masked. So in this case also, the studies which are conducted to form a different analog were also found to have poor activity or inactive. Okay, this was the first drug design strategy. And then I'm getting some background noise. Can we please mute our mics? And the second strategy is drug extension. So with drug extension, what we are saying is that they are trying to add extra functional groups, to the lead compound. And in our case, a lead compound is morphine. So they're adding different structures to morphine to kind of extend it. And why are they doing so? They're extending it because they want to kind of discover new binding regions in that binding site. Like a receptor has got a specific binding site where different analogs or different compounds will go and bind. So in our case of this morphine, once you extend it, you add different functional groups. you want to try and discover new binding regions inside that binding site. And out of this strategy, a few analogs were discovered. And the first one, the first compound where they had to introduce a hydroxyl group at position 14 of morphine, they did find that there was activity was seen, and this suggested that there could be some extra, hydrogen bonding interaction that may be occurring. Let me just take you to the structure. Okay, so this is an analog which was made out of this drug extension strategy. Remember, like here, when you look at this morphine, at this position, we have an hydroxyl group. And later on, they removed this hydroxyl group because initially we did mention that this hydroxyl group was not really necessary for analgesic effect. So meaning it can actually be replaced as you try to come up with different analogs. So because of that, they did come up with this oxymorphine, which was found to be about 2.5 more active compared to morphine after introduction of this, introducing this group. And once it was introduced now, you find that they did discuss, they made a conclusion to say if activity was increased after introducing this new group, it could be that there are extra binding regions which are found in these opioid receptors, where this new hydroxyl group is able to go and bind. Okay, and the other example is where now they tried to add. We are still talking about drug extension. Okay, they're still trying to extend. Still trying to add extra functional groups to morphine to try and see if they can find extra binding regions within the receptor. Of which now the second example, this is where we have alkyl substituents. I'm sure we all know what alkyl substituents are. This is where we talk about methyl, ethyl, propyl, isopropyl, and so on and so forth. So they're adding these alkyl substituents to the nitrogen atom. And remember, we did mention to say nitrogen atom was or is one of the cardinal functional groups in morphine that are needed for morphine to be able to produce its activity, analgesic activity. So meaning even as we try to extend this the structure of morphine to come up with different analogs, we need to have that at the back of our minds to say that we need the nitrogen atom to be maintained. So as they were adding an alkyl substituent to this nitrogen atom, they did notice to say, as they were increasing the chain, from methyl, that's CH3, to butyl, okay, the activity was dropping. It actually dropped to 0, which is what we have here with butyl. After adding butyl, that's about 4 carbon atoms, a chain having 4 carbon atoms. They discovered that the analgesic activity was completely lost. And besides that, also they did notice that after butyl, when they added a pentyl or hexyl, this is where you have about 5 carbon atoms or 6 carbon atoms. The activity was kind of now recovering. Okay, and besides those points, they also did notice that with the addition of a phenyl ethyl group, this is another benzene ring added to ethyl group. Okay, the activity of the new analog was quite high. It was like 14 times more compared to that of morphine. Like as seen here. Okay, this is the N-phenyl ethyl morphine after the addition of this ethyl phenyl group. So this group, after the addition of this, or after the extension of morphine to form this new analog had was 14 times more active than morphine. And the conclusion was that with this extension that was made, they assumed to say this new um, uh, uh, new group was able to interact with a certain hydrophobic region, because this one is hydrophobic. So meaning it's able to interact with a certain hydrophobic region, which is part of the opioid receptors. Okay, and okay, all right. So in conclusion, all we are saying is that with drug extension, it can help you have a better binding. Once you have it can help you discover new binding regions of a receptor, which can be helpful to improve the analgesic effect of your new analog. Okay, and also just some of the few outcomes also as a result of drug extension that I've put up these ones. There was after the attachment of an allyl group and a cyclopropylmethylene group, there was they came up with these two drugs, which are naloxone and naltrexone. And I'm sure some of you might have come across these two drugs. So with the addition of an allyl group at the nitrogen atom, they formed a naloxone. And then addition of cyclopropylmethylene group on nitrogen atom, they came up with a naltrexone drug. Okay. So, but the interesting thing was that after addition of these two separate groups, the two drugs which were formed were actually antagonists to morphine, and because of that, you find that because they're antagonists to morphine, they are now used in a clinical setup when somebody has, let's say, morphine overdose. They can give them naloxone so that it goes and binds to that receptor, and after binding to that receptor, morphine will have no access to the receptors, hence helping to manage overdose and also helping the addicts to wean off the addicts from their addiction of morphine. Okay, so this is how these two drugs were discovered. So we see that with the use of this drug extension strategy, working on morphine, they actually came up with these two drugs, which have been very useful in our clinical setup to kind of antagonize the effect of morphine. And these are the structures of naloxone and also naltrexone. Okay, and next, there's another strategy, of coming up with different analogs. So this strategy is called simplification or drug dissection. So what it is that, as we all know, we did mention to say morphine is quite a complex structure, and it has about six. It has got about 5 rings and other substituents. So because of that, it's really difficult to kind of to actually synthesize this compound in the laboratory. So because it's difficult to synthesize it in the laboratory, you would want to, as you are coming up with different analogs, you would want to kind of remove certain parts of that lead compound that may not be really needed in the desired activity that you want. So the same thing would apply to morphine analogs, where you look at the structure of morphine, and because studies have shown you exactly what parts of morphine are really needed for the analgesic effect, you can actually remove certain parts of it so that you kind of simplify your structure, making it easier for you to synthesize the structure in the laboratory. So because of that, the first study which was carried out under simplification of the structure was the removal of ring E. Okay, so this is the structure of morphine, and the ring E, this is where we have a ring attached to, the nitrogen atom. But again, remember we did mention to say with the nitrogen atom, it's an important group of morphine, which is needed in attaining the analgesic effect of the compound. So these scientists, they kind of removed this ring E, to see if there will be any impact, or if there will be activity which will be maintained. And at the end of it all, they did notice that after ring E was removed, there was loss of activity. So this was a no-go area in coming up with a new analog. Then the other one is talking of removing of ring D. Okay, so this is ring D. Ring D, this is where we have an ether bridge. Okay, so after they removed that ring E, the compounds that you make after removal of ring E are called morphinans. Okay, so with morphinans, they did notice that actually, after they made these morphinans, they actually still maintained their analgesic effects. And the conclusion was that if the removal of this ether bridge did not have an impact on the analgesic effect of the new analogs, then the ether bridge or oxygen bridge was not really necessary for the activity of the lead compound. So an example of these morphinines is N-methylmorphinine, which was actually found to be about 20% active, compared to morphine. And a kind of the reduction in activity was associated to the absence of the phenolic group. So let me just show you the structure. So this is the N-methylmorphinine. Okay, so this is N-methylmorphinine, and we are saying that the ether bridge was removed. After removing the ether bridge, this N-methylmorphinine had about 20% activity compared to that of morphine. And the reduction of 20%, like the conclusion was that it could be as a result of the loss of, hydroxyl group, like the one here, because we did mention that hydroxyl group was cardinal for the analgesic effect. So its loss might have an impact on the loss of activity, which was seen with this morphinine. Okay, the second example of the drug is levofanol. So with this one, it was found to be about 5 times more potent than morphine. But again, the side effects were still high. But we are making new analogs because one, to maintain the analgesic effect of morphine, but reduce the side effects. But that was not the case for morphinine. That was not the case for levofanol, which still had increased side effects. And besides that, it could be taken orally, and had longer lasting effects in the body. So when you look at this structure of levofanol, yes, it's a morphinine, okay, because it doesn't have an ether bridge here like the one with morphine, and the hydroxyl group it's still there, unlike this one, N-methylmorphinine, which did not have an hydroxyl group there. So this one was about 5 times more potent than morphine. So this also supports the conclusion to say we don't really need the ether bridge, okay, for analgesic effect. Okay, and in summary, all we are saying is that with these morphinines, these are the compounds that we've said do not have the ether bridge. So these morphinines are actually more potent and longer lasting than morphine. Okay, but they still have these increased side effects. And but the good thing with them is that they are easier to synthesize. Why is that so? It's because they have a reduced number of rings. All right, and then the other a strategy under simplification of these morphine structure was the removal of ring C and D. Okay, so with the removal of ring C and D, which are, let me take you back. Okay, so this is ring C and ring D. So with the removal of these two rings, the compounds that you make are called benzophoramines. Okay, benzomorphines. And with these benzomorphines, we are saying that they do retain, after you remove the ring C and D, these benzomorphines still retain the analgesic activity. And an example of this drug is metazocine. So with metazocine, we find that it still has the same activity as morphine, meaning it has maintained the activity. Okay, and the other example of the drug is phenazocine. So with this one, it's actually 4 times more potent than morphine. Okay, so with that in mind now, okay, these are just the structures of the drugs. So this is metazocine. So metazocine does not have this ether bridge ring and the other ring. So it only has 2 rings. And we're saying that's equal activity to that of morphine. But with phenazocine, we notice that there is a remove it is about 4 times more potent than morphine after they had added that phenylethyl group there. Okay, which is kind of similar to, we did look at another compound where we had added the phenyl. I don't know if I can find it, but anyway, there's another compound previously where we talked about the addition of phenylethyl group, and it was quite more potent than morphine. Okay, so in summary, all we are saying is that ring C and D are not essential for analgesic effect. Hence, if you have to make an analog which is smaller in size and easier to synthesize than morphine, you can actually remove ring C and D. And yeah, the activity is actually the same as that of morphine. All right, then the other strategy is, like in the terms of simplification of the structure, is removal of ring B, C, and D. So with the removal of B, C, and D, you give a compound called 4-phenylpiperidine. And examples of the drugs are pethidine, and this is a drug that is there in our setup, and it's used mostly for in childbirth, you know, and it has got a very rapid onset of action and quickly and a quick duration of action. And why is that important? It's because, you know, we are giving it to mothers, and you find that it can, like, if it was lasting, if the duration of action was quite long, you find that it can actually lead to respiratory depression in the babies. But because of its short duration of action, it will be easily metabolized and leave the system before causing an impact on the babies. And besides that, it still has the same anxiety side effects that we see with morphine, and the activity is about 20% that of morphine. So this is just the structure of pethidine. So we see that just having 2 cyclic rings is still enough to still maintain the analgesic effect of morphine, of the lead compound like morphine. Okay, so you can see that there is a decrease in the activity of pethidine, mainly because there's no hydroxyl group there, which is needed for its proper binding on the receptors. All right, and the other one is fentanyl. Also fentanyl, which is fentanyl, you find that it also has a reduced number of like there's the other rings have been removed, but still it still maintains activity, analgesic activity, and you find that it's about 100 times more potent than morphine, you know, and it still lacks the phenolic group, but it's very lipophilic. And just look at the structure, how it is. So because it's very lipophilic, it's able to cross the DB layer and have an impact. Okay, so with in summary, with these piperidine analgesics, we are saying they still have the same binding. You know, they still bind. They still bind to these analgesic receptors, but kind of differently compared to how morphine binds. And they still have these side effects of addiction, respiratory depression, and because they still act on this is new receptor. Okay, so our conclusion would be ring C, D, and E are actually not essential for analgesic activity. Okay, and what about removal of rings B, C, D, and E? What's going to be the impact? So the removal of these rings would make a drug called methadone. I'm sure most of you have heard of it. So methadone has got a similar analgesic activity to that of morphine, and it can be taken orally and has a fewer side effects compared to morphine, but like emesis and constipation, but the side effects of even including side effects of euphoria, sedation, withdrawal symptoms are less compared to those of morphine. And because of that, it's actually used also in addicts as you are trying to win them off morphine and the heroin. So this is just a structure of methadone and also morphine, trying to compare how the two structures to compare the two structures. And so we're talking about the different strategies that can be used in from coming up with different morphine analogs. So the fourth strategy is called rigidification. This is why you are trying to kind of make your compound rigid so that its conformations are reduced. And what we mean by that is that with your compound, certain molecules are very flexible. Okay, meaning they can be in different orientations in space. But with rigidification, you're kind of trying to make it rigid so that it does not move around a lot. Okay, but so with this strategy, you want to still make it rigid, but still maintain its active conformation. You know, a molecule can be active in this conformation, but not active in the other conformation. So you want to maintain that active conformation, which is needed for it to act within the desired receptors, to bind to the desired receptors. And because of that, you know, the strategy will help you to increase the activity of the new analog, to improve the selectivity of this new analog, and also to decrease the side effects. So an example of a drug that was formed out of this strategy is called etophine. So with this one, you find that it's actually about 10,000 more potent than morphine. You know, why is that so? It's because it's very hydrophobic and it can easily cross the BB layer about 300 times more easily than morphine. Okay, and you find that it has got a very strong affinity for these receptors in beta binding interaction. And actually, because of that, you find that it's actually used in immobilizing these big animals like elephants. Just a few mils of this drug etophine, you can, after inject an elephant will just become immobile. You know, so that's how strong this drug is, and this is coming about after you after making the molecule more rigid, that is less flexible, but still maintaining its active conformation. And this is the structure of this etophine. All right, so it becomes a bit hectic for a chemist to synthesize the compound. We've talked about drug extension, where you're trying to try and identify the different some of the new binding regions within the receptor. Then we also talked about what else? We did talk about which one? Drug extension, simplification. Then we talked about variation of substituents. I think those are the ones that we talked about. Then now we can go to the new concept, which is the theory of analgesics. So with this one, basically, what it is that with the theory, the receptor theory of analgesics, there are these different theories which talk about maybe like the numbers of receptors which are there, and also just basically talking about the receptor and how the drug is supposed to bind. So what we need to know is that there are about 4 different types of receptors, you know, which morphine and its analog can interact with. But among these 4 receptors, the 3 of them are the ones which actually have which produce the analgesic effect, while the other one would just produce maybe what does it produce? This other side effects, okay, which is basically mostly hallucination. Okay, so All right. So with the different theories of receptor binding, the first one that we talk of is the Beckett-Casey hypothesis. So this hypothesis talks about, it says that there is this rigid binding site, like the binding site has to be rigid for morphine to go and interact, or its analog. And as it is interacting, it's forming the analog of analogy of key and lock and key. Okay, so what they are saying with this bucket case hypothesis is that your morphine, we did mention that it's with these different compounds, others can be rigid, others are kind of flexible. So in the case of this hypothesis, they are saying the binding site is rigid, and once your compound or your morphine or its analog binds to that rigid binding site, they form this lock and key. Okay, so there is no movement or some sort, and you know how lock and key has to work. It has to fit properly for the door to open. The same thing was hypothesized by with this theory, where they're saying your molecule or your compound has to be bind to fix in a rigid form for the effect to occur. Okay, so now following these binding interactions, this hypothesis, the following interactions were proposed. Okay, so the first binding interaction which was proposed was that there has to be the presence of that basic nitrogen, okay, and that nitrogen that is on morphine, okay. So there has to be a basic nitrogen atom on morphine which should be able to ionize at physiological pH. I'm seeing messages on chat. I'll attend to them. Let me just finish up, then I'll attend to them later. Okay. So so the nitrogen atom has to be there on morphine or its analog, and this should be able to ionize at physiological pH to form a positively charged group. Okay, so with the basic nitrogen, what they are saying is that it has to go and form an ionic bond with an anion group, because once this nitrogen atom becomes ionized, it forms a positively charged cation. Okay, so because it's positively charged, it has to go and form an ionic bond with an ionic group, which is a negatively charged part of the receptor binding site. So this was the first binding interaction that they proposed. The second one was that the aromatic ring, the benzene ring of morphine has to be properly oriented, with respect to the nitrogen atom. That is, it has to be in a specific conformation, specific arrangement, in relation to that nitrogen atom. Why is that so? Because it has to interact with the binding site, forming these van der Waals interactions. Because it's hydrophobic, even the binding site has some hydrophobic location, which should be able to interact with this. We should be able to interact with this binding, this aromatic ring, which is found in morphine. Okay, that's the second proposal. Then the third interaction proposal, which they came up with, was that the phenol group, that's the hydroxyl group, the one which is bonded to benzene. It has to be hydrogen bonded, to a specific site, a specific place or specific region within the receptor. Okay, so that was the third proposal. Then the fourth interaction proposal, which they came up with, was that there has to be this hollow, kind of like a hollow shape, kind of, on the receptor, which should be able to accommodate that ethylene bridge. The ethylene bridge, that is the bridge that we have, where we have that ether bridge. So they're saying this receptor needs to have this hollow where this ethylene bridge should be able to fit in for the molecule to be able to interact well with the receptor. Okay, and then okay. So, but what are we saying? What's the conclusion with this Beckett-Casey theory? You know, the Beckett-Casey theory you're saying is a theory which talks about a molecule of morphine or its analog to be able to fit like a lock and key at the receptor, where they've talked about the aromatic ring should be in a certain position for it to interact well with the hydrophobic part of the receptor. The phenyl hydroxyl group should be able to have hydrogen bonding interaction with a specific part of the receptor. Then talk of the nitrogen atom, which should be a basic one, so that it becomes ionized, that is positively charged, and be able to interact with a negatively charged part of the receptor. So these are the proposals which were there. But again, what's the conclusion? So this theory kind of faced some doubts, you know, amongst other scientists. Why is that so? The first one was that when you look at fentanyl doesn't have that bridge, you know, that ethylene bridge. So the bridge is, for most of you, some of you might have forgotten, this is the one we are talking about. This is the bridge. Okay, so we are saying with fentanyl doesn't have that bridge. And if it doesn't have it, why is it that it's able to produce the analgesic effect actually is it 100 times or what? Times more than morphine, you know? Why can it be so? And yet we are saying with the Beckett-Casey theory, they are saying it has to have this ethylene bridge for it to fit well in the receptor. So that is the doubt which came about. And then the other one, where they talked about, we also have the other doubt which came through by other scientists, where they are saying there is also an extra binding. There are these extra binding regions, you know, which are found in the receptor. And how is this conclusion coming about? This is when you look at the other molecules that we talked about. We did talk about extension, you know, the drug extension, where we're adding these different long chains on the nitrogen atom. But why is it that even after adding those substituents or these other groups, why is it that those new compounds were actually, or analogs, were actually maintaining their analgesic effect? You know, if you are telling us that no, this receptor has to be rigid in a certain form, it should not go beyond a lock and key theory, you know. So these are the doubts which came through, and people and scientists kind of started, they were not really in support with some of the concepts which came with this Beckett-Casey theory. So the second theory is about the multiple analgesic receptors. Okay, where they are saying with Beckett-Casey theory, they are saying there's only a single receptor, but the other theory will tell you that there are actually multiple analgesic receptors. Okay, like I mentioned before, we have about 4 receptors in the brain where morphine or its analog can act, but only 3 of them have produced the analgesic effect. And you find that with these different analogs, and so with the receptors that I've mentioned, there are about 3 types of receptors. Okay, so the first one is called the mu receptor. So we find that with morphine, it actually binds strongly to this type of receptor, the mu receptor. And that's why you have the production of analgesia, the analgesic effect of morphine. And also, besides that also, we find that with this mu receptor, once morphine binds to this receptor, the side effects like respiratory depression, euphoria, and addiction, they are actually produced out of this receptor, okay, not the other type of receptors. So because you notice that once morphine binds to this receptor, this same receptor, that's the receptor which is producing the analgesic effect, and it's also the same receptor which is producing the side effects of respiratory depression, euphoria, and addiction. So you notice that it becomes difficult to, you know, to get rid of the side effects, because the morphine that you're making on the different analogs, they find that they become so strongly attached to this receptor, which is actually producing the undesired side effects of, yeah. Then you have got the kappa receptors. So the kappa receptors, you find that morphine doesn't bind so strongly to this kappa receptor. But again, it's the one which is associated with the side effect of sedation. Okay, that's kappa receptor. And we have got delta receptor. So delta receptors actually, you find that even these endogenous painkillers, you know, but these endogenous compounds in our bodies, which are produced by our bodies, which are able to help us with pain, they also together actually bind to this alpha receptor. And you find that morphine also can bind strongly to this receptor and bring out the analgesia. Okay, so this is just an example of, can you please mute Mike? So this is just an outline of these different activities of the different compounds and where they bind. So we've got morphine, we're saying it binds strongly to mu receptor, binds a bit less to kappa and a bit less to delta receptor. We've got methadone, which just binds to mu receptor. Pethidine, more of mu receptor, a bit on the other ones. Utropine, you find that it binds strongly on actually all of them, fentanyl, and so on and so forth. So this is like, you can take a look at them and see how the drugs are able to bind to these different receptors. And this, depending on the receptors where they are binding, the side effects also, the side effects are dependent on where these analogs are binding. So this is just an addition where I wanted you to see that we actually have endogenous opioid peptides. These are the endogenous compounds which are produced in our bodies, and they still have the effect of pain relief. You know, we have, these are the examples of enkephalins, endorphins, and so on and so forth. And these ones, they actually act on these receptors that are found in the brain. And besides that also, it just makes a conclusion to say, I mean, morphine is coming from plants. How is it that something that you are making out of plants has got, is going to act in the brain and find the receptors in the brain? It means that there could be something else. There's some other compounds which are found in the brain, which are, which we are born with, where certain compounds which are produced in our bodies are able to bind, you know, and that's how they discovered these endogenous opioid peptides, you know, because there's no way we can have receptors in the brain which are meant for morphine, which is coming from the plant. So, and with that analogy, that's how they came up with it. Scientists discovered these endogenous opioid peptides, which actually work on those receptors in the brain. Okay, so like the enkephalins that I talked about were actually the first ones to be discovered as the endogenous opioid peptides, and they have preference for delta receptors where they act. And while dinophins have got a preference for kappa receptors, endorphins can act on both delta and mu receptors. Okay, so this graph, I just wanted you to take a look at comparing the two structures. So we've got this net enkephalin, which is enkephalin, an example of an endogenous compound which has got the relief, this endogenous opioid peptide, and our morphine, which we are getting from plants. So if you compare, you see the similarity coming in there. Okay, so that's why they're able now to interact, to act on the same receptors and produce the analgesic effect. All right, so this is the end of this topic on opioid analgesics.